Hello, everyone. In this video, let me show you how to solve USAPhO 2021 Problem B3. Okay, let's first look at part A. So part A tells us the following thing. So we are given the hemisphere. So basically, this is the half ball, right? And then we have point mass, right? It is connected to a spring that is at the North Pole. So the relaxed length is 0. The spring constant is K. Okay. So the position of the ball is characterized by using the following general coordinate data. Okay. The mass is M. So in part A, we assume that although, so this is a hemisphere, is the half of the sphere, right? But in part A, we consider a simplified model, assuming that so the ball can only just make the circular motion. That is, we just need to consider this plane. Okay, we don't have to consider the 3D graph. Okay. So the problem says that depending on the value of the spring constant K, there are different numbers of the equilibria, and they are with different types in terms of whether they are stable or not. So it asks us to fully characterize all scenarios. So for what ranges of K, that corresponds to how many equilibrium, and whether some equilibrium is stable or some is unstable. So it asks us to fill out this form. Okay. So we observe that this system actually is a conservative system, right? Therefore, for such a system, one way to analyze an equilibrium point and to determine whether it is stable or not is not to just do the complicated force analysis. We don't have to do it. So we can just simply analyze its potential energy. So we know for such a system, when it is conserved, right? So if the first order derivative of the potential energy is 0, it means that this is the stable point. This is the equilibrium point. At this point, you would take the second order derivative, and it is positive, then it implies it's a stable point. If the second order derivative is negative, then it implies that this equilibrium point is unstable. So we'll take this perspective to analyze the problem. The reason we want to do that is because, if we analyze the force, right? So there are multiple forces. They are in different directions. So we have to do the vector analysis. And also, so in order to see whether it is stable, so you still have to deviate from the equilibrium point and reanalyze the problem. It's very complicated. But if we take the energy perspective, so we just analyze a function with scalars, no vectors, right? And we just do the simple first, second order derivatives. So everything is just a purely math. So it's just basic math. Okay, so that will save our effort a lot. Okay, but before going into math, I still want to develop some physics intuition about why for different cases we may have different equilibria, and they may be with different types in terms of their stability properties. So let's think about it. Suppose for one extreme case that the spring constant K that is super small is pretty close to 0. What's going on? Oh, by the way, of course, we know for different K, we always have one equilibrium point. That is the North Pole at the top of the bowl, right? So it's obvious, it's trivial case. Okay, so let's see whether we have some other non-trivial solution. So if K is very small, so if you slightly perturb it from the top of the ball, what happens? Because K is small, so even though the spring might be extended with a long length, but it still doesn't have a very strong force to hold the ball. So finally, the ball will roll downward to the floor, right? So basically, we can only have just one equilibrium, just the top point. And this is definitely unstable, right? Because the force exerted by the spring is very small. And let's consider another extreme case that the spring constant K is super large. So think about it. So I give you the spring, the spring constant is very big. So when you slightly deviate from its rest position, so it has a strong force to pull you back. Therefore, in this case, there is no way for this ball to move away from the top point, right? So we have a unique equilibrium, and it is very, very stable. What about the case in between, when K is not so small, it's not so big? So it is not so big. It means that when you perturb from top position, so it should go down to some extent, right? And after moving down to some angle, then we know that the spring has already been stretched for a decent length, right? And then we know that because the spring constant K is also not too small, right? So that means, so with a decent length, it exerts enough force to hold the ball, to avoid it to further sliding downward, right? So then we reach an equilibrium. So that might be a middle position, and that should be stable. And because of the symmetry on the left side and the right side of this hemisphere, so we should have these two additional stable equilibrium. So that is about the physics insight in this problem, okay? And next, let's formalize our analysis by using the aforementioned energy approach. And then finally, we will see whether the result we derived from mathematical analysis is consistent with our physics intuition. All right, so let's write down the energy. And to characterize the position of this ball, we know we only need to use one general coordinate, that is theta, okay? So energy is a function of theta. It consists of two parts. One is the potential energy stored in a spring. So at angle theta, the length that has been extended by the spring is equal to the length of this arc, right? So r theta. So the square is r squared theta squared. And the second type of the potential energy is the gravitational potential energy, right? Suppose we use the ground as the reference plane. So the gravitational potential energy is mg r cosine theta. Okay. Next, let's find our equilibrium. So we take the first order derivative, and we see that for what theta it is equal to 0. Let's take its derivative. So let me just write down the result, okay? So the first order derivative takes the following form. Okay. So this is the first order derivative. And we will see for what theta is equal to 0. So we'll do it in a moment. And because later we still have to compute the second order derivative. So let me first compute it out and put it here. And later we will use it to check whether it is positive or negative at every equilibrium point. So this is equal to this, okay? All right, so let's look at the first order derivative and see when it is equal to 0. So we just need to look at the parentheses, right? There are two terms. So obviously there's no closed form solution. So maybe the good way to find the number of equilibriums is to draw a diagram of the functions of sine theta and theta. Okay, let's do it. So sine of theta is pretty simple. And recall we just need to consider theta is from negative pi to pi, right? So let's see how this function looks like. No, it's a very bad plotting. Something like this one, right? So this is function sine of theta. And then we have another function that is the linear function of theta, right? So the slope is this one. But you know the slope is very complicated, right? So to avoid it to complicate my analysis, let me just call it, say, lambda. Okay. So what is lambda theta? First, we always know that it passes through the origin, right? Because its intercept is 0. What about the slope? So here's the thing, because we want the first order derivative of b is 0. So now we just need to draw. So we already have drawn the sine function. So we need to draw the function lambda theta. We see that at how many points these two functions cross. So we know that depends on our slope lambda. Let's first think about it intuitively. So first, when lambda is very small, we know this line is very horizontal, very flat. So they only meet each other at the origin. And when you slightly increase lambda, think about the graph, right? So what is the threshold value? The threshold value happens here. Right? So the coordinates of this point is pi over 2 and 1. So basically, when lambda is increased to a level that the red line passes through this point, then before that, because the line is very flat, so we have just a single solution. But after it passes it, so you think about it, if you continue to rotate the red line counterclockwise, so then there will be 2 more meeting points, right? So think about it. So 2 more points, one might be somewhere here, the other is here, right? 2 more points. And then you keep on rotating the red line. And then we know that for the function sine of theta, you look at its first order derivative, or we call this the slope at every point. So it cannot be more than 1. It is equal to 1 when it happens at 0. So it means that when you keep on rotating the red line, and when it's equal to 1, so the slope is equal to 1. So when the slope is equal to 1, then we know that for positive theta, it is tangent to sine theta, and to negative theta also tangent to it. So actually it's tangent to sine of theta, right? At point 0. So it means when lambda is equal to 1, so let me call this lambda as lambda, say lambda star, okay? So when lambda changes from lambda star to lambda is equal to 1 in this range, so there are 3 solutions. And when lambda is equal to 1 or is above 1, so it just had a single solution, right? That is the origin. So now we have a very clear picture about the number of equilibria, okay? So let's put it down here. Okay, so let's compute lambda star. So for lambda star, we know lambda star times pi over 2 is equal to 1. So lambda star here is equal to 2 over pi. So now we have a clear answer to this question, right? So for lambda, if it is less than pi over 2, the equilibrium is 1. It's just the origin. When lambda is bigger than or equal to pi over 2, but is less than 1, we have 3 equilibria. One origin, one is for positive theta, the other one is for negative theta. And when lambda is at least 1, so we have a single equilibrium. That is theta is equal to 0. Okay? All right. Next, let's see that for each equilibrium, whether it is stable or not. So we have to check the second order the derivative for each solution of the first order condition equation. Okay. Let's look at the first case. So recall that. So this is just a lambda. Okay. So let's look at the first case. So in this case, we know the only solution is at the origin. So theta is equal to 0. So cosine theta is equal to 1. Okay. So here lambda is no more than 2 over pi. So this number is less than 1 minus 1. So this is a negative number, right? So for the first case, v double prime and 0 is a negative number. So it means that the only equilibrium is unstable. For the second case, we'll go back in a moment because it has some non-trivial solution. Let's then look at the easier one, the third case. So the only solution is at theta is equal to 0. Let's see. So again, it's called lambda minus 1, right? For v double prime. So lambda here is bigger than 1. So this is positive. Therefore, this solution is stable. Next, let's go back to the second case, that is non-trivial case. So we have 3 equilibria, and we have to analyze them separately. Let's look at the simplest one, where the equilibrium is at the origin, which means theta is equal to 0. Okay. So let's look at v double prime. This is lambda minus 1. Because for the second case, lambda is still less than 1. So lambda minus 1 is negative. Therefore, this equilibrium is unstable. Okay. And then let's analyze the other 2 non-trivial solutions. So let me again draw the above diagram here. Right? So here we have some non-trivial solutions. One is here, the other is here. Okay. So, because of the symmetry, so they should have the same stable type. Either both are stable or both are unstable. So we just need to analyze one. With the other lots of generality, let's analyze the positive theta. Okay. And for this one, so let me call this at theta naught and see what we have. Okay. So for theta naught, then we know that lambda theta naught is equal to sine of theta, right? So that's the definition of theta naught. So basically now we want to see that for theta naught that satisfies this equation, what about v double theta naught? So we need to analyze the sign of lambda minus cosine theta naught. Is it positive or it is negative? To do the analysis, let's plug lambda from the red equation into this green equation. So we get this term. And for this term, the question is it positive or is it negative? Okay, so how do we know it is positive or it is negative? Well, so now the problem boils down to compare this number and this number, which is positive, right? How to compare these two? Nobody likes a fraction because here we just consider positive theta 0, right? So it is equivalent to multiply both sides by theta naught to compare sine of theta and cosine of theta times theta, and see which is bigger, which is smaller, right? Which is bigger, which is smaller for these two? Well, let's do the following thing. So to compare these two, right? So it is equivalent to find the sine of this function for theta. That is from 0 up to pi over 2. So let's check the sine of this function. So this is one observation we have. For theta is 0. So this functional value is 0, right? So let me call the function f of theta. So first we know f of 0 is 0. And then I want to find out is moving trend when theta is positive. So let me compute the first order derivative of this function. So it's equal to cosine theta. What about the first order derivative of cosine theta times theta? So it is equal to cosine theta plus sine of theta, right? Wow, this is so good. Why? Because we notice that for theta that is in 0 and pi over 2, sine of theta is positive. That's really amazing. So that tells us that for this function f of theta, when theta 0 is 0, when theta is positive, so because first order derivative is always non-negative, so it keeps on increasing. So it means that f of theta is always positive for theta is between 0 and pi over 2. So that implies that the second order derivative of this equilibrium point theta naught is always positive. So it implies that this equilibrium point is stable. So that is the analysis of this part. All right, then let's go to the next part. So the next two parts are actually separated from the first part. So recall that in the first part, we just restrict our focus onto a two-dimensional move. We're actually, so that, the degree of freedom is just 1. So it's just a circular motion. But for the rest of the parts, we allow the ball to make the spherical motion, okay? So we have to look at a 3D diagram. It's more complicated, okay? All right, so let's look at this one. So actually, this graph is very misleading. Don't just look at it from the 2D perspective, but look at it from the 3D perspective, okay? So let me draw the 3D diagram for you, so then you know what I'm talking about. And also, because it's making a spherical motion, later you'll see that we have to use the spherical basis. Therefore, I don't want to just draw the hemisphere. Let me make it a complete sphere. Okay. So it says the following thing. Suppose this is one latitude. Okay. All right. So the problem says that here we have the initial velocity at the equilibrium point we have identified above. Say we have identified the equilibrium point at where? Theta naught, right? So we start from somewhere here. Say this point. Okay. All right. So starting from here, it says that our initial velocity here is along the line of constant latitude. So let's just think about this horizontal plane, so that corresponds to a given theta naught, right? So this is our initial velocity. Is on a tangential direction, okay? So basically, this is the correct diagram. This is a way to understand this. Okay, so it's not 2-dimensional, but 3-dimensional. Okay. All right. So this problem asks us to determine its initial trajectory in the following way. So, if we do not have this initial velocity, and from the analysis in the previous part, we know that this position is an equilibrium, is a static position. So the net force is 0. But now I give it the initial velocity in direction B, in the latitude direction, right? So I'm wondering that after a short moment, whether it remains on the given horizontal circle that corresponds to the same latitude, that is, it moves towards direction B, or it will go up to the North Pole, or it go down to the equator. So what could be the trend after gaining an initial velocity? So to answer this question, of course, you can do the rigorous analysis, right, by writing down the general acceleration formula, but you don't have to do it. So we could just use our physics intuition to get the result. Okay. So this is the way that I analyze this problem. So actually, suppose it moves up, say, following trajectory A, or go down by following trajectory C. So it's very hard to characterize them, right? But perhaps the simplest way to characterize it is we hope is follows trajectory B, because it's just making the circular motion on the horizontal plane. So that is perhaps the simplest scenario. So given that, I want to do the following analysis. So I want to first assume that trajectory B is correct. That is, this particle is making a circular motion on the given latitude. And then I will see that whether we could get a consistent forces, or we cannot get the correct forces that will make it happen. And then suppose it is violated, we cannot get a net force that supports this circular motion. We will see what is violated. And then we get a sense about whether the particle's trajectory will deviate from B and how it deviates from B. Okay, that is how we analyze the problem. All right. So because basically this scenario happens at the thin knot, right? We know that initially, before gaining the initial velocity, the knot is an equilibrium. No, so we call it, it's an equilibrium point, right? So let's start from there and see after gaining the velocity, what happens afterwards. So let's do the following diagram, okay? No, I don't want to use the back color. Let me change it to a different color. Okay, suppose the initial point is here. And let's draw the free body diagram. Okay, so we have the following forces jointly applied at this object. So first, we have the gravitational force. Second, we have the normal force that is in the radial direction of the sphere. Third, we have the tension exerted by the spring. So what it points to? So we know that the spring actually has one end fixed here. But the direction of the force is not a connection of the red dot and the blue point, because it's curved on the surface of the sphere. So at the particle here, right? So it should be on this tangent direction. That is the tension, okay? So we have these three forces. And we know that at the thin knot, before gaining an initial velocity, the net force is 0. So the sum of these three forces is 0. Okay. All right. So next, let's see what's going on after this article gains the initial velocity. And also suppose after gaining the initial velocity, we assume the correct trajectory is the yellow one. And it moves on the horizontal plane in a circle. Suppose this is true. Let's see what we should have. Well, suppose we make this circular motion. Because the radius is fixed, right? It's a circle. And also, at this latitude, we know that the spring doesn't change its length and has the same distance towards the ground. So its total potential energy is not changed. Therefore, its kinetic energy is unchanged. So its speed is constant. So to make a constant speed circular motion. Therefore, it has the centripetal acceleration. That being said, after gaining the initial velocity, so the sum of these three forces should point toward the left, right? And that serves as the centripetal force. And let's see that immediately after gaining this initial velocity, which of these three forces might be changed? For gravitational force, it's always the same. For the tension, no, it depends on the distance between the mass and the one endpoint, the red point, on the surface of the sphere. So it doesn't change, right? But how we gain the horizontal direction centripetal force? The only way is from the change of the normal force. And then for the normal force in here, so let's look at is x component. So by having the centripetal acceleration or centripetal force, right? Because the centripetal force is in the negative direction of the x-axis. So it requires us to reduce the normal force, right? Because the normal force, you see that, so its x component is positive. So it has to be reduced such that the x component net force is going to the negative direction of the x-axis, right? So let's think about it. What happens afterwards? Suppose you want to decrease the x component of the normal force. Because its direction of the normal force hasn't changed. So let's say this is the z direction. So this is to the change of the magnitude of the normal force. And then we look at its z component. So the z component of the normal force goes down, right? And now let's look at the z component net force. Because the z component of the tension and the gravitational forces are unchanged, but the z component of the normal force decreases. So the z component net force becomes negative, right? So that being said, the mass should have a downward force. So it has a downward acceleration. Therefore, it implies that it cannot follow the yellow trajectory. That is trajectory B. So no way. Because it has a downward acceleration, so its trajectory must be C. That is the answer to this part 1. Next, let's look at part 2. So part 2 asks us to compute the total radial force, okay, on the mass and time 0. Okay, so how we compute it? Well, so actually we can directly apply a very basic result. it says the following thing. So this is what we know. Suppose in a two-dimensional plane, 2D plane, right? There's a mass that is making a circular motion. So then we know that as long as the distance towards the center is unchanged, say it is equal to r, right? Suppose this is the normal direction, ER. Then we always have that the normal force, or let me write the acceleration. So the acceleration in the ER direction, or the radial component acceleration, is always equal to negative of, because your velocity is always tangential, right? So it cannot have the radial component velocity. Otherwise, we cannot keep the equal distance towards the center, right? So v squared over r. Okay. The negative sign means that in the radial direction, it points towards the center. So we have this centripetal acceleration that is from the circular motion. And actually, we can use the spherical coordinate system to rigorously prove the fact that this result can be extended to the spherical motion. Okay, so now let's think about the left-hand side diagram, not just as a circle, but as a sphere. Okay, so maybe one way to think about it as a sphere is, yeah, let me draw some latitude and longitude. So it looks like a sphere. Okay, so for spherical motion, as long as you keep the same distance toward the center, right? So basically, your velocity is always in a tangential direction, right? So then we have the same radial component acceleration, the same thing. So then for this part, you just apply this formula so that you can see what we have. Okay. I'll still use this free body diagram. And for this free body diagram, recall that what is theta naught? Recall that theta naught is defined as this one, right? So then basically we know that, yeah, let me draw it here. So theta naught, so let me put it down here. And n points towards the center of the sphere, right? Okay, and also recall that this is theta naught. So that means this is theta naught, right? Okay. So now we should put our focus on the radial direction. Right? Yeah. So basically, oh, yeah. So actually, I did much more than that. We already done. We don't have to do the force analysis anymore because the problem just simply asks us the total radial force. So we are done. Yeah. So we got acceleration and multiplied by mass. So the radial component net force is just equal to AR times M is negative mv squared over r. That's it. Right? So we don't need this anymore. Okay. This is not for the, so the problem doesn't ask us to compute N or T, but if you ask us to compute the initial normal force, so we can use the radial component acceleration to compute it. So it's an easy job. Okay. All right, that's part B. Then let's move to part C. Wow. This is very complicated. Again, so this diagram, I don't like it. It's very misleading. So I'll draw the 3D diagram for you. Okay. So this says the following thing. So we put a cylinder with a very small radius r. You see, it's very small, right? on top of the sphere. So this is how the 3D diagram looks like. So I don't know the height, but yeah, maybe it has some height. I don't know, but I know the radius is very small, something like that, right? I put it on top of the sphere. Suppose the mass is launched at an angle alpha away from the direction of the spring displacement. So what that means? Well, so it means the following thing. So think about what if alpha is 0? So what that means? What is the direction? So because here we have to analyze a 3D system, and also the trajectory is on a sphere. So maybe we have to use the spherical coordinate system. So as you can see in this part, so we have to use both the Cartesian coordinate system and the spherical coordinate system. And sometimes we have to make the transformation between these two, okay? So let me use the language of the basis in the spherical coordinate system, okay? All right. Let me draw the latitude. And then let me draw a longitude. Okay. All right. Suppose the mass is here initially. Okay. So what is the velocity? So this is the center, right? So let's first draw the spherical basis. So we know this is ER, right? And then along the longitude, so the tangent going downward is E theta. And on the horizontal latitude plane, right? So this tangential direction is E phi. So those are the basis of the spherical system, right? So when we say V has this angle, and it means that suppose the alpha is 0, then it means that V is on the same direction or on the same line as E theta, but in the negative direction, okay? So V can be written, the vector form can be written negative V times E theta unit vector. So that is for alpha, that is equal to 0, okay? And if alpha is equal to 90 degrees, what it means? So it means that it's totally perpendicular to the unit vector E theta. So think about it. If you are perpendicular to this longitude component, and you are making spherical motion, which means that you can't have any radial component velocity. So the only direction you can move is you can only have the E phi component velocity, right? So that is a latitude component velocity. So that is the two extreme cases for alpha is 0 and 90. So now we have an understanding about how to decompose the vector into the component vectors, right? For any alpha. So for any alpha, we make the following decomposition, right? So basically, it tells us the following thing. For the initial V, it is written as the longitude component vector is negative V cosine alpha times E theta plus V sine alpha times E phi, right? So now we have a very clear picture about the initial velocity, right? So we not be confused about is the direction, okay? All right. So then let's further look at the problem. So in the sense that by getting initial velocity, so we have the kinetic energy. So the problem asks us to express everything in terms of it. So this is fairly simple. So we know it's just equal to 1/2 mv squared. So in the rest of analysis, actually it's easier to use v. And maybe in the last step, we'll write v in terms of k, right? So this is a small thing. So the answer is to find the maximum angle alpha max at which the mass is launched from its equilibrium point. We call that state null, right? So then it could hit the cylinder. So what that really means, let's think about it. So why you can hit the cylinder? In what sense? Well, think about it. Suppose I fix v, fix the speed. If alpha is 0, then so your initial movement direction is on the longitude direction, right? So you move directly towards the cylinder. So then you could hit it, right? By contrast, suppose your alpha is 90 degrees. So your initial velocity is on the latitude direction, as I shown on the previous problem. So you even gain acceleration downward. So it's pretty far away. There's no way for you to get to the top. It's not good. So that is the intuition why alpha cannot be too big. There's a threshold alpha, such that you can just hit the cylinder. If it is bigger than that, there's no way for you to get to the top. So what that is equal to, okay? All right. So now we fully understand this problem and we understand the initial velocity. So everything is fully understood. It's pretty good. Then let's formally solve it. It's not good to write down the dynamic equations by, just doing force analysis and compute acceleration, compute the trajectory. Is very complicated. So maybe we could think about whether we could find some conservative physics quantities. Let's try. So for the spherical motion, for many such problems, actually the system is conserved, with the angular momentum. But maybe not the full angular momentum, but maybe some component of the angular momentum, or it is conserved on one direction. Okay. So I'm claiming that for this problem, so the z component angular momentum is conserved. Okay, so you see that I have to frequently switch between the spherical coordinate system and the Cartesian coordinate system. So the opposite direction, this is the z direction, right? So then this is x, this is y. I'm saying that the z component angular momentum is conserved. Let's see why. Okay, so let's first compute is the torque and see that. So basically we can show in any position on the sphere, if the torque doesn't have the z component, so it implies that the z component angular momentum is conserved. Let's see. So what is the torque? When the mass is at any point. So let's see here, right? So the mass is at any point. What's the torque? So let's do the force analysis, right? So what forces this mass experiences? But the torque is essentially R. So it is equal to R times ER times the net force. One is the gravitational force. Another one is the tension. Another one is the normal force. We have three forces. So for the gravitational force, is in the negative z direction. What about the tension? So recall from the previous part, I showed that the tension should be on the longitude and it points towards the North Pole, right? So the direction of the tension is the negative side of E theta. So we have this one. Then what about a normal force? It is always on the radial direction. Okay. So let's compute this and see what we get. So for the first one, so it's negative R mg ER cross product Z. We'll treat it in a second, okay? And for the second term, ER times E theta. So in the spherical coordinate system, that is equal to EV, right? The unit vector on the latitude direction. And the third term, ER cross product ER is 0, right? So we have these two terms. Let's look at them. So recall that my intention is to show that the torque doesn't have Z component. Let's see whether it is true or not. First, let's see EV. Because EV is a unit vector in the latitude direction. The latitude, this plane is always perpendicular to the Z axis. So we know that EV is perpendicular to Z, right? And then let's look at the first term. This is a cross product. Something cross product Z. So if something cross product number, so the new vector is perpendicular to both of them. So this must be perpendicular to Z. So both of these two component torques are perpendicular to Z. It implies that in every moment, the torque is always perpendicular to Z. So this implies that the Z component angular velocity or the angular moment is 0. Okay? All right. So that will help us a lot to analyze this problem. Let's see how. Okay? All right. So let me draw the diagram again. Suppose that somehow, finally, you have the chance to hit the cylinder. Okay? You hit a cylinder somewhere here. Okay? And let me say the hitting point is called B. Okay? And let me assume that when it hits the cylinder, the velocity is called B prime. So let's write down the equation following from the conservation of the Z component angular velocity. So what is the Z component angular velocity at time 0? So let's go back here, right? So V takes this form, right? So let's compute it out. Let's see what is the initial angular momentum, and then we take it Z component. Okay. Cosine was angle alpha. Okay, cosine alpha. Okay. For the first term, ER cross product E theta, that is equal to E phi. Okay. For the second term, ER cross product E phi is equal to ER cross product E phi is equal to the negative of the is equal to the negative of E theta, right? The negative of the negative of E theta. Okay. And don't forget that we are only interested in the z component. So recall that, as I explained before, if phi is the latitude unit vector is perpendicular to z. So it doesn't contribute to the z component. So we don't need to look at it anymore. And then we just look at E theta, right? And let's see what about is z component. So for E theta, let's say here, right? The spherical diagram. So let me put in this position so it is clear. Suppose the latitude here is 0. So then E theta is just here, right? And yeah, it's here. And recall that initially the angle here is theta 0, right? So then what about is z component? So this is theta 0, right? All right, so that is equal to a negative of sine of theta 0, right? So negative canceled out, so it's positive. Okay, so that is the initial z component angular velocity. And then we know that in the final state, when the mass hits the cylinder, so this physics quantity is conserved. So let's compute that one. Okay. mr. So let me first write it in the vector form. Okay, and then we will treat it in some way. Cross product. Well, for R, actually, so I know when it hits the cylinder, it's the point B. So let me write it in terms of OB. Okay. First V. And we just care about this Z component. Let's see what we get. So what is OB? Because recall that the radius of the cylinder is very, very small, right? So let me assume that the North Pole is denoted as A. So A and B should be very close to each other. So why don't I write OB in terms of OA plus AB? And for OA, we know is in the Z direction. So let me write it in this way. Cross product B prime. Then we take the Z component. So for OA, it's already in the Z direction. So the Z component after doing the cross product with B prime is 0. So we just need to look at the cross product of AB cross product B prime. Okay. So how this one looks like. All right. So this is the key thing. So we know that the radius of the cylinder is very, very small, right? So given this fact, we can approximate that AB are on the same horizontal plane. Okay. So this plane you can understand is to be tangent to the North Pole, but there may be some gap, but because it's very small, and also you could treat, say, the cylinder has some weight, so it has the contact list, the interaction with the actually it closely contact with the sphere, the surface of the sphere. Okay, so no gap. You can just think about it in that way, making that approximation. Okay, so basically you could treat AB to be on the XY plane. Okay. All right, so think about it. Okay. what that is equal to. Well, so actually, this problem asks us to do the following thing. So we want alpha to be maximized, right? So let's think about the following thing. So when alpha is maximized, it means that, so for bigger alpha, so when alpha is too big, we cannot even go up to the top of the North Pole, right? So it means that at this threshold point, B prime doesn't have its z component velocity anymore. So it's purely on the xy plane, right? Sounds good. And in addition to that, since it is on the xy plane, right? So actually, to get it at alpha max, the threshold alpha, so we want this cross product to be maximized, right? So then we know that it's maximized when AB and B prime are perpendicular to each other. And what about AB? So when it hits the cylinder, right? So we know it is pretty close to the North Pole. Then recall that the angular momentum in z direction is conserved. So it requires us to have a very big speed. But we want to find the threshold alpha. So basically, V should not be too big, right? It's at a threshold value. So then we want the AB to be as long as possible, right? So the longest distance between A and B is the radius of the cylinder, so it's smaller, right? Therefore, this is the z component angular velocity, angular momentum when the mass hits the cylinder. So we established one equation here, the yellow equation. Okay. All right, so this is one equation. But you know, here we have the following variables. We have alpha, we have B prime. So to solve the problem, we need to establish the second equation. What's the second one? So let's further think about if there's any other physics quantity that is conservative. The answer is yes. So we have the conservation of the total energy, right? So we can use that conservation to help us write the second equation. Okay. So what is the initial total energy? Recall that we have the following kinetic energy. We have the potential energy stored in the spring. And we have the gravitational energy. So for the gravitational energy, because here I'm drawing a full sphere, so let me use the horizontal plane that passes through the equator, so the equator plane as the reference plane, okay? So plus mgr cosine theta now. That's the initial energy. What is the total energy when the mass hits the cylinder? So the kinetic energy becomes B prime square. And when it hits the cylinder, so we know that it's pretty close to North Pole. So their distance actually determines the potential energy stored in the spring. So that is negligible, okay? And another energy is the gravitational potential energy. So mgr, okay? So we write the second equation that follows from the energy conservation. Again, in this equation, we have variable B prime so actually this is even good. So we don't even need to use alpha anymore, right? So we just have B prime. We can compute it out. That is great. We love it. Okay. All right. So by having these two equations, so finally recall that our job is to compute alpha. So we can compute it out. And also don't forget that in our analysis, we use the initial velocity v. But the problem asks us to express the final answer in terms of the initial kinetic energy k. So then after getting the formula for alpha in terms of v, we then convert v into k. Then we are done. Okay? All right. And after doing some algebra, I will skip the intermediate steps. So let me write down the final answer. So the final answer takes the following form. It's very complicated. Okay, that is the answer to this question. And actually, so before concluding this video, so I have some comment on this part. That is, when I first write this problem, so recall that the problem said we put a cylinder with a small radius on top of the North Pole. So I was very confused about this setting. Why we have to put a cylinder on top of it? Because finally we want this mass to hit a cylinder. So my initial intuition is, because it's so small, can we just neglect it, right? And to rephrase the problem as has some initial velocity, we'll finally hit the North Pole. What's wrong? It seems to be the reasonable intuition, right? But why this part complicates my thinking process? I'm very confused in the very beginning. I don't know why. And then I realized why we need the cylinder, because without having it, we'll be in trouble. So here's the reason. First, I want to explain it from two perspectives. First is from the math perspective. Let's look at the final result and see where is the radius of the cylinder. Is here, right? So let's think about a case. Suppose we don't have this cylinder, which means that small r is 0. Then what this result tells us? It tells us that in order to hit the North Pole, your alpha must be 0, which means that your initial velocity must be in the longitude direction. You cannot have any alpha. No, you can't have any latitude component, right? So if that is the case, you can see this makes this problem to be results to be trivial. Nobody likes it. It's not fun. That's from math. What is the intuition from physics? Here's the intuition. So recall from our earlier analysis that we have shown that for the complicated motion of this mass, so its z component angular momentum is always conserved. It doesn't change, right? So what is the z component angular momentum? If we put our focus on the xy horizontal plane, then basically that tells us that, so regardless of where the mass is, so on the projection to the xy plane, we should always have a non-negative or non-zero or positive, and it's non-zero angular momentum or the angular momentum, right? So how we have it? Right, how we have the angular momentum. So we should have the following two conditions. One is that the xy plane component velocity cannot be 0. And the second, on this projection plane, the distance between our reference point and the position of the mass cannot be 0. Otherwise, if we have the xy plane or horizontal velocity, but we don't have the horizontal displacement, then you will take the cross product to compute the angular momentum. You'll get 0, right? Therefore, for this problem, you were to get a non-zero z-component angular momentum. So we must have some displacement from the vertical axis to the mass, right? I mean, the displacement is on the horizontal component displacement. We must have some positive displacement, right? Therefore, to satisfy this condition, this problem was designed in a way that we have to put a cylinder on the sphere. Otherwise, there's no way for us to get a conservation of the z-component angular momentum. Or we could just get this trivial result, right? That alpha is 0.